Welcome to the UCF Drone Delivery Challenge for Senior Design. Team Black includes Lauren, Jasenia, Justin, Zachary, and Brandon. The advisor for this challenge is Scott Layton.
Why was the drone delivery project chosen? Since 2010, various retail companies have been testing and implementing drone delivery. Walmart and Amazon have teamed up with drone delivery companies like Wing and Zipline to deliver goods to consumers. Walmart and Amazon have completed thousands of deliveries using drones safely and effectively. Using drones to deliver goods has many benefits, including faster delivery times, lower cost, fewer emissions, and flexibility. Drone delivery companies have expanded their partnerships to food retail companies like DoorDash to deliver meals from restaurants to consumers. The drone delivery challenge focuses on the engineering process developed to safely and efficiently create a prototype of a drone that is able to deliver packages. This project requires students to create a prototype and a model while conducting risk assessments, analysis, and testing. The goals and objectives for the Drone Delivery Challenge require students to deliver rotorcraft-based drones for the purpose of delivering packages. Teams in the competition will select motors, rotors, and mounting applications to optimize vehicle performance. They will also research and model payload mechanisms as well as design and analyze and build vehicle structures to deliver maximum efficiency for range and product delivery. The vision for this project would also allow fast food restaurants to deliver food packages by unmanned, short-range delivery vehicles. Drone delivery will dramatically extend restaurants' customer base as it adds flexibility and convenience to society. For this specific project, the drone competitions require a drone to deliver as many packages as possible within 30 minutes. There will be 4 different delivery points varying in size. The team that delivers the most weight in the time limit will win the challenge.
Once the teams were finalized, a project manager was selected and the team came up with the contract to structuralize the project. The project mission and goals were set, and the team came up with basic ground rules to hold each other accountable throughout the project timeline. Roles and responsibilities were discussed and set for each team member, and the project stakeholders were recognized. The team then came together and listed topics to research for modeling and prototyping of the drone. Each team member researched specific components and parameters needed to build and understand how drones work. After researching, the team created a list of user wants and needs and analyzed them to determine what specific characteristics are needed to efficiently complete the project. Once the engineering requirements were laid out, components were selected and the design was modeled to create a concept generation. A proposed Gantt chart was created to outline the project plan. This Gantt chart changed throughout the project timeline to fit the team's schedule. The team created a table for failure modes to analyze the potential failures and how they would affect the goals of the project. These risks were rated by priority and actions were recommended in order to reduce failure. Before the proposed drone design was implemented, modeling and analysis of components were generated. The team created an electrical diagram to identify the amount of electrical components needed for the drone. eCalc helped determine the compatibility between components, and FEA analysis was conducted to determine strength and structures. In the prototyping and testing phase, each component was tested thoroughly to achieve optimal performance. Once the drone was assembled, the most important part of testing was the PID tuning. After the PID tuning, the team did a series of flight tests and practiced the routes needed for the competition.
Analysis and assessment of a model is important to prototyping as it gives insight into the compatibility between components, placement of components, and the components in structural integrity. eCalc is an online RC calculator for the flight performance. It provides accurate calculations based on the vehicle's weight and component characteristics. The eCalc determined the hover time for the drone to be approximately 13 minutes, the risk of components overheating, which was low, the thrust to weight ratio, the motor efficiency, and other key parameters. The electrical diagram created helped determine the placement of each component on the drone frame to optimize the connections. Flow trajectories were simulated to determine if the structure of the drone and components would be able to generate enough lift to hover off the ground. Structural analysis was conducted on the landing gear and arms of the frame. It determined the structures yielded safety margins above the required margin requirements of at least 1. Once the analysis conducted supported the component's compatibility, Assembly and placements of the components began. The team began by putting the frame together and the landing gears together using the screws and bolts. We decided on the placements for the internal electrical components. Each component was placed strategically on the frame to achieve optimal connections between them. After the placing of the internal components, the top plate of the frame was added and the wiring was connected and manipulated for the cosmetic look. But for conducting flight and competition testing, each motor was tested on a thrust bench. The team used a 3D printed stand that could adhesively stick to a scale. Activating the motors added negative weight to the scale. The weight equals the amount of thrust each motor produces. Each of the motors produced about 4,000 grams of thrust, which exceeded the calculated max thrust needed to lift the drone off the ground. While PID tuning, the drone was suspended by cable wires off the ground to test the roll and pitch without repeatedly crashing the drone. To test the yaw, the drone was suspended by a single cable wire attached to the bottom of the frame. The drone would then be able to hover a foot off the ground to minimize crashing. Once this was done, the PID tuning testing was complete. The team began testing the cargo release mechanism by adding different weights and practice for the competition routes.
To set up the flight controller, the team used Q ground control to begin vehicle setup and optimize the flight performance. The compass calibration included setting up the orientation of the drone. It required the drone to be turned in specific directions in specific positions. The radio calibration connected to the transmitter to the flight controller to ensure the drone mimicked the movements of the pilot. In the flight mode section, a kill switch and an arm switch were selected for safety. The team inputted the battery characteristics into the battery selection section, which allowed Q ground control to read the correct percentage of the battery. In motor calibration, the position of the motors were inputted based on the relative distance between the flight controller and the motor. Then each motor was tested in order to select the correct motor position and direction. The minimum frequencies of the motors had to be adjusted to ensure each motor was spinning at the same time and velocity. Now, for the PID tuning, it was the most tedious part of the testing phase. There was a lot of trial and error between each test. Q ground control mainly focuses on the rate controller and the attitude controller sections. Starting with the rate controller, the overall multiplier, differential gain, and integral gain were set for roll, pitch, and yaw. The attitude controller sets the proportional gain for roll, pitch, and yaw, and each of these values were lowered due to the high responsiveness that we were receiving from the drone during test flights. The velocity and position controllers generally didn't need much adjustment, and once the drone was stable, flight tests were conducted to practice for the UCF drone delivery competition.
Some wider implications of the drone delivery include creating a new business opportunities, reducing delivery costs, reducing emissions, and increasing efficiency of delivery. Consumers and producers enjoy less contact between transactions and the convenience of faster and flexible deliveries. Also, drone usage is continuously growing in today's industry. Researchers believe that drone usage will continue to grow in the next decade. Now here are some test flights. In this test flight, the drone is armed and takes off with the package attached to the cargo release mechanism. The drone is pitched towards and moved towards the drop-off location.
And in this test flight, the drone is armed and it takes off. The drone is pitched a few feet forward with the package attached to the cargo release mechanism. And once the servo is activated and the mechanism released the package, the drone had to land on the ground. And it was guided back to the beginning and safely landed.
Thank you for watching.
Woo!